Section 2.2 on page 123, we are going to talk about vectors in 3 dimensions. Now, 3 dimensions, of course, is we live in a 3-dimensional world where we have the plane, but there's also a 3rd dimension that is we have come to x, y, and z. Now, z, there's a question as to which way is up. Okay, and because z can be on the up schedule or the down one. Now, to make that distinction, we're going to use some trick called the right-hand rule on the next page. What happens is you put your hand out, okay? Your fingers start at x, okay? The x coordinate, You swing it to y, and look at where your thumb points. The way the thumb points, that's the positive z direction, and that's the convention that we use. So you always see x, y, z, the positive axis is going that way. Okay, so start at x, swing it to y, and look at where your thumb is pointing on your right hand. So this is called the right-hand rule. All right, so next, let's look at example 2.11, where there's a point in space. X is 1, y is minus 2, and then z is positive 3. So you flip to the next page, and very soon you can see how that is graphed. You come out in the x-axis by 1, then you walk towards the y-axis by negative 2. So you walk on the negative direction of the y-axis. So far, you're still on the xy plane. And then the last step is you need to go straight up to in the z-axis 3 units. And that is your final location. That's how you plot any point in 3 dimensions. Now, the 3 dimensions has 3 basic planes, as you can see on page 125. The bottom plane, the planes are named by the coordinates. That is the one on the level is called the xy plane. That's the one we normally use before we got to 3D. And then there's also the xz plane and the yz plane. As you can see, those are just the planes defined by the main axes. Okay, next page. The distance. Okay, next, let's look at theorem 2.2. The distance between 2 points in space. That distance is given, it looks very similar to the Pythagoras theorem, and it is defined as the differences of x, y, and z coordinates. You calculate the differences, square them, and then take the square root. So it's like the Pythagoras theorem, except you have one more thing to worry about, which is the z coordinate. The proof of that theorem, look at the next page. We're on page 127. The proof of that theorem, actually, you probably have done it already. Okay, I can't believe you haven't done this at some point in your life. What happens is you have 2 points, okay, P1 and P2. They are in space, however, but basically they're the corner of some box. Now, how would you calculate the distance? Well, first you calculate the distance of the bottom diagonal, which is what? What is that? D1? Yes, and with that, and with the height of the box, you can calculate the entire diagonal distance. So you apply the Pythagoras theorem twice. And I'm positive you've done this at one point in your life in, I don't know, maybe 8th grade or something like that. Anyway, so that's how you calculate the distance in space. And that's example 2.12. Please do that as part of your homework. Next, let's look at page 128, where it mentions 2 obvious points. That is, in space, on the plane, 2 lines. If 2 lines are not parallel, they have to intersect. But in space, that is not the case. 2 lines can be not parallel and yet never intersect anyway. See, because you got space. You can lift it up and pass it without actually crossing it. So that's all you're doing. And the same way with circles, right? You have 2 circles. They can cross each other without touching, ever, right? That is, anyway, you get the idea. So space has certain qualities because of the 3rd dimension that the 2D cannot perform, okay? In 2D, you 2 circles like that, they are going to cross at some point, or 2 lines. But in space, that is not necessarily true. All right, so then on page 129, let's consider how to describe stuff in space. For example, in in our regular 2D dimension, the equation x equal to 0 is just the y-axis. Now what is it in 3D? In 3D, x equal to 0 describes the entire plane, the zy plane, because for that entire plane, it doesn't matter what y or z is, x is 0. So something like, and similarly, z equal to 0, okay, you just imagine that just means your point can be anything as long as its z coordinate is 0. If that is the case, then it's just is every point on the xy plane. And then next, if you have the y equal to 0, what is y equal to 0 in space? That means everything that x and z can be anything, okay, as long as y is 0. So you imagine all the points where x and z coordinates are both 0, and that would be the plane of x and z, because the xz plane has all points, has all kinds of x and z's, but the y is 0. So that's how y equal to 0 describes that plane. And so next, let's look at other stuff. In the following place, all right. Now, as a result, then you can, for example, if you need a plane that is, I'm looking at page 130 here. Let's look at some rules here. Yeah, okay, fine. Let's look at these rules. Now, the first rule says the plane in space that is parallel to the xy plane, that's the normal one, right? And contains some point ABC, some random point, can be represented by the equation z equal to c. That's because as long as the third coordinate equals to c, then it contains the point, and then all other coordinates can be anything you want. It will be the same thing. And then the other two rules apply similarly. So please do example 2.13 as part of your homework to find out parallel planes, I guess. Next, let's look at page 131, where you have a sphere. Now the sphere, the 2D sphere is a circle where the circle's equation is x squared plus y squared equals to some positive number. Now in 3D, the situation is the same, except now you have the third dimension. So you have x minus a plus y minus squared plus y minus b squared plus z minus c squared, that equals to some kind of r squared, where r is the radius of your sphere. Now that is, and ABC is where the center is located. So that is the equation of a sphere. And with that, please do example 2.14. And next, example 2.15, same thing. You got the diameter of the sphere. So you have to figure out what the center is. And the center is at the midpoint. The midpoint is you have to divide stuff by 2, okay? And locate it. Subtract the 2 points divided by 2 to figure out where the midpoint is, and then come up with the equation of the sphere with the center at the midpoint. And that's, so please do example 2.15. Next, other things in 3 dimensions. All right, that is a quick problem of you have some kind of equation, whereas I'm looking at 2.16, where you have some kind of equation that multiply to be 0, which means it's 2 planes, and where x equals to 4 or z equals to 2. And then, yeah, eventually you come up with a plane. Next, let's look at even more stuff. What is that? Well, other equation, 2.17, we have a regular circle, okay? X minus 2 squared plus y minus 1 squared equals to 4. Now that is a circle on the 2D plane, but what is it in 3D? It doesn't say what z is. If it doesn't say what z is, that means z can be anything, okay? I mean, each of these points on the circle, you can slap a z on there with any value, what that means is that eventually you get something called a cylinder. See, because z can be any value, up and down, any and all values of z for each value of x and y. So very soon, then you come up with a cylinder, infinite one, going up and down, is what that equation describes in 3D. Anyway, please do example 2.17 as part of your homework. Next, let's look at 3D vectors. Now, 3D vectors are no different than 2D vectors, except that it has a third coordinate, being that it's in 3D, but otherwise it works the same. You have a vector with 3 units, right? 3 coordinates, and they add up the same way. Each the x coordinate adds up with the other x coordinate, etc. And then if you multiply it by a scalar that is just a number, not a vector, then you just multiply that number with each coordinate individually. And then if you add or subtract them, you do the same way. Yeah, that's about it. So then, and also, there's what is this called? The standard unit vector representation is that you have, in the previous section, we mentioned I and j, which are unit vectors in the x and y direction. So now we have a third one, which is, of course, called k. K is the unit vector that goes up, okay? And every vector can be represented that way. That is, a vector that's called xyz can also be written as x times I, and then y times j, and z times k. Is how you can, they mean the same thing, really. It's just a different way of saying the same stuff. And with that, please do example 2.18 as part of your homework.